All right, here's a picture of some NASCARs kind of going from the straight and then enter a banked curve. This is like Bristol Motor Speedway, and it kind of shows you the radius of the circular motion. And what they're going to do is they're going to take this car and you're going to give a face down view, and then they're going to flip it, and it'll be on an angle. That's the version of what we're looking at when we go to the free body diagram here in a second. All right, let's take a look at the banked curve. And the first option we're going to look at is looking at maximum speed. So we're going to try to find an equation for the maximum velocity you can go around this banked curve. We are looking at a cross-section view. So the car is right here and it's coming at us. The normal force, of course, is perpendicular. Gravity, of course, is down. And if we're going really, really fast, then friction is going to go down the ramp. We're not going to tilt our coordinate system. So we have our vertical direction, and in this case, we're going to call that the radial direction, right? Our circular motion is like this, right? It's on that plane. There's no motion in the y direction, so all the forces must be balanced. And then we do have a centripetal acceleration, meaning there is a force making us move in a circle. And then that acceleration, of course, we can replace by v squared over r. So the two hard parts, the only hard parts of this is breaking down the vectors and then the algebra of getting rid of the normal force. So let's draw these separately. Okay, so these are the pictures. And I'm just going to use the normal force here. Okay, that whole thing is the normal force. Okay, but the normal force does two things. It pushes us inward and it pushes us up. This angle is some theta, with that angle being also theta. That is some alpha, which means this top angle is theta, which means that the up part of the normal force is adjacent, thus the cosine. That part is the sine. Okay, so now we have the normal force broken down into its inward piece and up piece. Let's do the same thing for friction. Friction's even easier. Friction is down the ramp. Okay, and what friction does is that it pushes us inward, but it also pushes us down. This angle is theta, that angle is theta, so this is FF cosine theta because it's adjacent to the angle, and this is opposite, so it's the force of friction times sine theta. Okay, once we have those two things established, the rest should go pretty easy. Again, the banked curve, there are three forces. The force of the bank itself, which is the normal force, acting perpendicular to the bank. Friction, and we know friction is going to go down the ramp because we're trying to drive really, really fast. And gravity. Gravity is down. We're not going to tilt the coordinate system like we normally do on a ramp, because on a ramp the acceleration is down the ramp, but on a banked curve the acceleration is inward. So we need this inward direction to be one of our coordinates, or one of the axes in our coordinate system. Okay, so let's do y hat. Right, the up forces. Well, the normal force has an up force. That's n cosine theta. And then the down force of friction, so minus FA sine theta minus mg, and that's equal to 0 because we know there's no acceleration in that direction. Okay? In the r direction, meaning the radial direction, we have an inward force of n sine theta, and we have another inward force of FF cosine theta, and we know that causes, that net force causes that object to experience centripetal acceleration, which I replaced by v squared over r. Okay, I'm going to take this top equation, and the first thing I'm going to do is rewrite the force of friction as mu n. Okay, and I'm going to do a couple steps at once to save me some time. I'm going to factor out this normal force. You know what? I won't skip any steps. Why not? So that's cosine. Now you know what? I am going to skip one step. I'm going to move the mg over. So I moved over the mg and I factored out the normal force. But then over here, then I know that the normal force is equal to mg divided by cosine theta minus mu sine theta. Okay, here I'm going to do the same thing. I'm going to rewrite the force of friction as mu times the normal force. And then I'm going to factor out this normal force. Okay, then I'm going to take this and substitute in for the normal force. So I'm going to get mg all over cosine theta minus mu sine theta times sine theta plus mu cosine theta mv squared over r. I'm going to cancel the masses, and then I'm going to I'm going to multiply both sides by r, so this r is going to pop over here. I'm going to write all this trig stuff over each other, right? I have this divided by this, so I have sine theta plus mu cosine theta all over cosine theta minus mu sine theta equals v squared. So then I got to take the square root. Okay, so the maximum velocity, you can go around a banked curve, is a function of the planet you're on, g, the radius of the curve you're trying to bank, the angle of the bank, and of course then the coefficient of friction between the tires and the road. Okay, and that's the maximum velocity you can go. Now, how about Vmin? Well, it turns out this is really easy, because if you go really, really, really slow around a banked curve, well, there's a chance you might actually slip down the bank, and so then friction would go upwards instead. So instead of being in and down, it's going to be out and up. So all you'd have to do is come over here and change that sign to positive, because it would be up, and this sign to a negative, because it would be in, and all that does is flip these signs. Okay, so then the minimum is the square root of gr sine theta minus mu cosine theta over cosine theta plus mu sine theta. Very easy to get the minimum velocity, because the force of friction just changes direction, and then just changes the sign here and the sign here, which then propagates through and really just changes those two signs. Okay, there is the banked curve. Probably the biggest thing is that you can break down these two vectors appropriately. You realize that you are not going to tilt the coordinate system. You're going to leave it with a vertical and an inward. And then you're going to do the same song and dance we always do. We're going to use this equation to solve for the normal force. We're going to rewrite friction as mu times the normal force, and then we're going to plug in, and then we're going to do some algebra to get to that point. There are a few textbooks that take, let's get even a different color here. How about blue? And they'll take this guy, and what they'll do is that they'll divide everything in this fraction, top and bottom, by I think they divide it, yeah, they divide it by cosine. So then you get GR, and if you divide everything by cosine, this is going to be a tangent, and this is just going to be a mu. So tangent theta plus mu. And if you divide this by cosine, you're just going to get a 1 minus mu tangent. So if you saw that in a book, this and this are the same thing. All I did was just take this and this and this and this and divide all of them by cosine to get that. So if you see that, then it's the same thing. I think this is fine though. Okay, so hopefully this answers questions on the banked curve, that you can find maximum velocity. If somehow instead of the maximum velocity they wanted the maximum angular velocity, then again you would need to know that v equals omega r. So if you knew the r value, then if you know how fast you can go, then you can know how fast you could actually rotate or spin on that banked curve.